Now, yesterday we talked about this idea that in this formula about centripetal acceleration, v squared over r, that v, speed, has an exponential relationship with acceleration. It also has an exponential relationship with centripetal force. Okay? So if I'm going around a corner, like the exit ramp, the on-ramp here that gets you back onto Highway 2, okay? If I go around that corner at the recommended speed, which I think is 60 kilometers an hour, okay? I go around that, I have no problem. There's plenty of friction to hold me in the corner. The corner is banked, okay? And when you bank a corner, we're going to talk about this later today, but when you bank a corner, you essentially make it an inclined plane, okay? And so when you're going around it, you push on it, and it pushes back. And some component of that is pointed back towards the center, so it gives you additional centripetal force. That's why, like, high-speed NASCAR racetracks always have these really steeply banked corners. Okay, it helps them to take them faster. Okay, so if I take that corner at the regular speed, I have no problem. There's plenty of force to keep me in the corner. Okay, but if I double my speed and try and take that corner, all right, unless I have a car that's designed to maximize my cornering ability, I am probably not going to make that corner, right? Because now I need how much more force to hold me in the corner? 4 times as much. It's an exponential relationship. Okay? I double my speed, I need 4 times as much friction to keep me in the corner. And it's unlikely that I'm going to get that provided to me by my tires in the road. Okay? Especially if conditions aren't ideal. Right? Everybody okay with that idea? Yes? Okay. So the other way, okay, to take a corner would be not to change my speed, but to take the corner wider. Okay? If I take the corner wider, I'm changing the radius of the corner. Right? So if r becomes bigger, v stays the same, and r becomes bigger, what's going to happen to a? It's going to get smaller. Okay? Now, if you've ever seen, like race car drivers, when they take a big corner, okay, so they've got a corner like this, okay, they start out here on the outside of the corner, okay, and they take this corner like that, okay. They can do that faster than somebody who tries to hug the inside. Okay, why is that? Well, the reason is the radius of this corner is this much. The radius of this one is that much. By taking that more straight line, arced kind of path around the corner, they've effectively made the corner bigger. And so as a result, okay, they can traverse it without sliding out. Okay, that sort of makes sense? All right, so radius has an inverse relationship with centripetal acceleration and thus with centripetal force. Okay? The bigger the radius, the less centripetal force would be required and the less centripetal acceleration would be experienced. Right? So if we look at these two corners and we just compare them, okay, one has a radius of 320 meters, the other has a radius of 960 meters. Okay? Let's look at what the centripetal acceleration of each one of those corners would be, assuming we take them both at 28 meters per second. Okay? So if I do that for the first corner, that's going to be 28 squared divided by 320. All right, so the centripetal acceleration for that corner is going to be 2.45 meters per second squared. Okay, that's considerable. Okay, like you would really feel that. Okay, you'd be pushed to one side of the vehicle, okay, on that corner. How much less is it going to be on the second corner? 3 times less. It'll be 1/3 of that value, because the corner has a radius that is 3 times bigger. Okay, so it's an inverse relationship. I make the corner 3 times bigger, I make the centripetal force 3 times smaller. Okay, so if I go 28 squared, okay, divided by 960, okay, I get that number, which is exactly 1/3 of the number I got before. Okay. All right, so that's what we just did there. Okay, and then we're gonna skip right over that. All right, move on to the next thing here, guys. And that is centripetal force, okay? Now, centripetal acceleration and centripetal force are related, okay? Because they're related through Newton's second law, okay? Newton's second law says that force, net force equals mass times acceleration. Okay? If something's moving in a circle, it's because there's a force pulling it where? Into the center, right. If something's going to move around the circle, there's a force moving it, pulling it towards the center because the object's always accelerating towards the center. Okay, so if that's the case then, is centripetal force really just net force? It's towards the center, right? Okay, it's accelerating towards the center. We always say that the acceleration and the net force are always in the same direction. So yes, centripetal force is essentially net force. And it can be calculated by going mass, but not times regular acceleration, times centripetal acceleration. Okay, so this is really just Newton's second law, but now it's applied to circles. Now, we just looked at a formula that said that centripetal acceleration is v squared over r. Okay, so our formula for centripetal force is mv squared over r. You will use that formula like m times a in the last unit. That's how much you're going to use it. Okay, it is Newton's second law applied to circles. Okay, that's the math of it. Okay, now we got to look at the understanding part of it. Okay, circular motion cannot occur if there is no centripetal force. There has to be a net force to accelerate the object towards the center and make it go in a circle. Okay, understand that lots of forces can act as a centripetal force. Okay, yesterday when I was using my ghetto physics demo, okay, the centripetal force was the tension in the string. Okay, if I'm looking at the moon orbiting the Earth, the centripetal force is gravity. Okay, that's what keeps the moon in orbit. That's what makes the Earth orbit the sun. Okay, there's a centripetal force being provided by gravity. Okay, you can have a centripetal force provided by normal force. Okay, normal force can act as a centripetal force. That's what the gravitron, okay, was doing. We watched the video of the guys inside that could stand on the wall. Okay, so as it's moving around and around, you're trying to leave the circle, but the inside of the circle pushes back towards the middle, and normal force can act as a centripetal force. Okay, friction very often acts as a centripetal force. Anytime you're even just walking and you turn, you are relying on friction to turn. Okay, friction is acting as a centripetal force. When you're driving, same idea. Okay, that's why when it gets slippery, it's harder to turn. Okay, if you come into a corner too fast and you turn your wheels, there's not enough friction, so you just go straight. Okay, just watch Canada's Worst Driver. Okay? They have this test that they do every single time. It's like the best episode in the whole thing. Okay, and it's an exact demonstration of this. They make this really slippery, like Teflon coated surface, and then they make them drive towards it at 50 kilometers an hour, and they have to make the turn. Okay, and every last one of them does what 90% of people do when their car starts to skid. Hit the brake harder, turn the wheel more, which are the two things that will result in absolutely nothing happening. Okay? You have to overcome your instincts in that situation, and you have to actually turn the wheel straighter and get off the brake. Okay? the whole purpose of anti-lock brakes, okay? If your wheels continue to spin, you have friction and you can turn, okay? If your wheels lock, you're just going in whatever direction the car was going before. They cannot steer if they cannot roll, okay? Think about that the next time you're sliding through a corner, okay? Think about what Mr. Coderre told you, okay? Get off the brake, okay? And don't crank, okay? If you crank, you will just go straight, okay? On an icy surface. All right, we're going to look at how centripetal forces operate. Pretty straightforward. They push or pull like any other force, but they're always towards the center. Okay, and we're going to look at banked curves, which is what I was talking about with the exit, the on ramps and exit ramps. Okay, those are banked curves. It's also how planes turn. Okay, how many of you have ever ridden on a plane before? Okay, when you're coming in for a landing, okay, what do you always notice about what the plane does? Right, it does this. Okay, tilts its wings. If a plane wants to turn, it has to tilt its wings. Okay, yes, there's a little rudder on the tail that does this, just like a boat's rudder does. Okay, but that's not making big turns for the plane. Okay, what the plane does is banks its wings and actually makes the lift that the wings produce act as a centripetal force. When it's doing this, the lift from the wings points towards the center, okay, and the plane can turn. Now, what does that mean the plane also does at the same time? When its wings are level, the lift produces a force up. When the wings are banked, some of that lifting force is pointing into the middle. What does the plane do anytime it banks its wings besides turn? It loses altitude. Yeah. Okay. Anytime a plane banks its wings, some of the lift, all of the lift is no longer lifting. Okay, it's turning, and so the plane will descend. That's why it does that. When you're coming into land, they bank their wings and they descend, okay, in a spiral, okay, in order to lose altitude slowly and comfortably. Okay, because they can't always just start descending from 100 miles away. Okay, there's lots of planes in the pattern. They have to circle for a while. All right. So centripetal force. Okay, this is what we just talked about a minute ago. Okay, centripetal force is really just the net force for an object moving in a circle. So it's mass times centripetal acceleration. Okay, and that means it is mv squared over r. Mass times speed squared divided by the radius. Okay, will get you the net force or the centripetal force, always pointing towards the center. Okay. In lots of cases, it's really easy to identify what's acting as a centripetal force. Okay. With the piece of tape on the string, it was obvious. The string was the thing pulling the tape back towards the center. Okay. It's not always obvious though. Okay. When we're talking about friction, that like somebody going around a corner, okay, people don't always realize when a car is going around a corner that it's what force is holding it there. Okay. They just see the car turning and there's nothing connecting the car to the center of the corner. Okay, it's actually the friction between the tires and the road, okay, that causes that to happen. All right, so the effective speed on centripetal force. So if we're looking at our formula, okay, our formula says that centripetal force is mass times speed squared over r. So just like we were talking about a little while ago, the effective speed on centripetal force is exponential. Okay? Any change in speed will result in an exponential change in centripetal force. Okay? If I reduce my speed by 1/2, I will have 1/4 the centripetal force. Okay? If I triple my speed, I will need 9 times the centripetal force. Okay? It's an exponential relationship because speed is squared, okay, in that formula. All right, so we got this model airplane, okay, and has a mass of 0.9 kilograms moving at a constant speed. We want to find the centripetal force, which is being provided by the tension in the line, okay, for speeds of 19 and 38 meters per second. Now 38 is 2 times 19. So my centripetal force, when I calculate this, they should be how many times different? 4 times different. Okay, I'm going to double the speed because it's an exponential relationship. I should need 4 times as much centripetal force in the second situation. Okay, so our first one here, we're going to have 0.9 kilograms times 19 squared divided by the radius, which was 17 meters. So 0.9 times 19 squared divided by 17. All right, so that's going to require 19.1 newtons worth of centripetal force. All right, second situation. Fc equals 0.9 kilograms times 38 squared this time, so double the velocity. Still on a 17-meter line. Okay, 76.4. That is exactly 4 times 19.1. Okay, so there's an exponential relationship. Remember that the next time you try and turn a corner really fast. Now, what's the effective radius going to be? If I increase the radius, what's going to happen to the centripetal force? It should go down, right? Okay. We got mv squared divided by r. If r gets bigger, I'm dividing by a bigger number, which should make Fc go down. Okay. Now, if we're looking at this, okay, as our example here. Okay. So, short radius, okay, it's pulling pretty hard. Okay. I mean, you guys can't tell that, but I'm holding it. It's pulling pretty hard with this short radius. Okay. Now, if I make it a lot bigger, and I make it go that fast, okay, it's going the same speed. Doesn't look like it because it's in a much bigger circle, okay, but it's also not pulling nearly as hard. Okay? So speed's the same, but because I've made the radius bigger, I don't have to pull nearly as hard to keep it there. All right, so if we're looking at that mathematically, okay, so we got a 28 meter per second speed here that we're looking at. Okay, so we'll have 0.9 times 28 squared divided by 11. Okay, that's going to give us our first Fc. Okay, so I get 64 newtons. If I double that to 22, my next number should be, if I double the radius to 22, Fc should go down by a factor of 2. Right? It's linear now. Radius isn't squared, right? Okay, so if I go 0.9 times 28 squared and now divide that by 22 instead of 11, okay, it's exactly half. Okay, it's an inverse relationship. R goes up by a factor of 2, Fc goes down by a factor of 2. All right, everybody okay with that idea? Okay, there's two kinds of curves that we're going to look at. Banked curves and unbanked curves. Okay, so an unbanked curve is level. Right? It's just a corner. So like any corner in town here, none of the corners in town are banked. Okay, they're all just corners. Okay, the only thing keeping you in an unbanked corner is friction. Okay, friction between your tires and the road is the only thing keeping you in a corner. All right. So if I go around this corner, okay, what are some things I can do that can maybe help me to take this corner faster? Okay, I could take it wider. If I take it wider, I increase R, okay, and then I could go faster using the same centripetal force. What else? Okay, I'm relying on static friction. Static means the two surfaces are not doing what? Means they're not sliding past each other. Okay? Static friction means there's no skidding going on, right? So if I'm like looking at one of the desks and I'm pulling on it, it's not moving, it's because I can't overcome the force of static friction. Once it begins to slide, then it's kinetic friction. Okay? The day Mr. Van Herve was here and he played the friction lesson, that was one of the things I said in that. Okay? Kinetic friction, the sliding, is always less than static friction. Okay? It's something we forget when it gets icy out here. We're trying to get up the hill. Okay? And I see people do the same thing every time, right? They just gun it. Okay? That's not going to help you get up the hill. You're relying on kinetic friction in that case and not static friction. The same is true for a corner. Okay? You want to take the corner fastest, maintain static friction. If you start to skid, you're going to continue to skid because now you're using a lesser frictional force of kinetic friction. Okay? That's why drifting won't do this as well. It'll look cooler. Okay? There's no arguing that drifting a corner looks way cooler than just turning a corner. But you never see Formula One racers drift during a race. Okay? Reason for that? It's not as fast. It looks cooler, but it's not as fast. Okay? Relying on static friction allows you to take the corner faster. Okay? Here's why. If I just go around this corner, that's my radius. Okay? If I drift this corner, okay, I'm having to swing the back end of my car out and then power on and create a driving force with the back wheels that points towards the center. Okay? Am I wasting a lot of the energy that my car can produce to help me go around and then accelerate after the corner? Yeah. Okay? If I just go around this corner, once I'm through the corner, I can just pound the gas and my tires are already hooked up. Okay? I'm going to move away quickly. If my tires are already spinning when I get around this corner, they don't provide me with as much friction and thus as much forward force because they're already spinning. Okay? And I won't get the same kind of a launch after the corner. Okay? Mythbusters actually did this. They brought in the Drift King guy. Okay? They did this, they built this track, and both Adam and Jamie took it in like an old Crown Vic police cruiser. Okay? And they did it without skidding. Okay? And they timed themselves. Then they had the Drift King do it, and he couldn't beat their times. Okay? Because every time he got around a corner, okay, it took the car a little extra time to get hooked up and power through to the straightaway.
Wasn't it slightly faster on gravel or something?
On gravel it can be, yes. Because on gravel your static friction's never working, you're always sliding anyway, which is why you see rally drivers drift corners. Yes. Okay, so it is different in rally, for sure. All right. Making sense so far? Big thing we have to remember here is friction provides the centripetal force for an unbanked corner. Okay? All right, so if that's the case, these problems work a lot like Newton's second law problems from the last unit, except a little bit easier. Okay? We've already said that Fc equals mass times centripetal acceleration. But it's also the vector sum of all forces. It's easier though because there's only one force here. What's keeping me in this corner? Friction. Okay, so my centripetal force is being provided by the force of friction, or friction is acting as my centripetal force. Everybody with me there? Okay, what's the formula to calculate friction? Mu times normal force. So for an unbanked corner, I'm saying Fc equals Ff, which means mv squared over r equals mu times the normal force. Okay, further to this corner's not banked, so it's level. Normal force is numerically equal but opposite in direction to what force? Gravity. Okay, so I can take this formula even further and say this. Agreed? Okay. So if I know, like this example gives me here, it says the radius of this corner is 50 meters, so I have r. It tells me mu, 0.9. Could I calculate how fast I could take this corner? What don't I have? I don't have mass. Look at the formula. What's on both sides? What'll happen to mass? It'll cancel. Okay? So what this is saying is, all things being equal, like everything's a box, mass doesn't matter here. Okay? It's only the coefficient of friction and the acceleration due to gravity that matter. Obviously, in the real world, that's not entirely true. Okay? It's not so much that mass doesn't matter, it's the distribution of your mass, or the location of it. Okay? Sports cars put their mass really close to where? To the ground. That's why all sports cars are low. Okay? That way their center of mass, or what we sometimes call the center of gravity, is really close to the ground. Semi-trucks have really high centers of gravity. If they take corners really fast, they tip over. It's not about losing traction, losing friction, it's about rotation. Okay? Conservation of angular momentum. They just tip over. Okay? And once they start to tip, okay, then obviously, friction starts to change because now their distribution of weight is off. Okay? And they just tip over. All right? But if you're really low to the ground, then you're not going to get that rolling effect. We're not even going into that because it actually becomes very complex to start factoring in things like body roll and location of mass. We're just saying everything's a box, okay? Because it's way easier to do that. All right, so I'm going to compare the maximum speed at which this car can take a corner in ideal conditions and icy conditions. Okay, now, obviously, under icy conditions, I have 1/9 the available friction that I would have under ideal conditions. Okay? So how much slower am I going to have to go, theoretically? A third. Exactly. Remember, speed has an exponential relationship. The square root of 1/9 is 1/3. Okay? Everybody with me there? Okay. So, here's what we're looking at. Okay? I'm going to manipulate this for V. Okay? So to get V by itself, I'm going to multiply both sides by R. So R comes over here. M's going to cancel. And then I'm going to have to square root. So to get V, V will be the square root of mu G R. Mugr. Okay? Square root of Mugr will give me V. All right, so if I plug in my numbers for ideal conditions, that's going to be that V equals the square root of 0.9, my coefficient of friction, times 9.81, my acceleration due to gravity, times the radius, 50 meters. So under ideal conditions, the car can take that corner at 21 meters per second. Theoretically, how slow is this going to have to go if I have 1/9 the friction? What's 1/3 of 21? 7? Yeah. Okay, so let's check that. Okay, so this would be, we'll call this dry, okay, dry conditions. And maybe we shouldn't use the abbreviation VD. Summer. Okay, and then we'll go V, winter. Okay, so we'll have 0.1 this time, times 9.81 times 50. Okay, exactly 1/3. Right? So if it gets icy, I have to slow down. Common sense. Everyone forgets at the first snowfall, but it's common sense. Okay? If I have less friction, I need to go slower. I don't have as much ability to corner or stop or accelerate, okay, or any of those types of things. Okay? Everybody all right with that idea? Okay, so unbanked corners, okay, rely on friction in order to keep you in the corner. All right, now banked corners. Banked corners in the real world also have friction, obviously. Okay, there's obviously friction in a banked corner because you got your tires and the road surface, so there's friction. But the corner's also banked. Okay, and when we bank a corner, as I was saying before, we essentially turn it into an inclined plane. The reason we do this is twofold. Okay, there's actually two reasons that clover leafs and interchanges are designed with banked corners. Okay, the first reason is it guarantees a safe speed regardless of the road conditions. Okay, if they bank a corner, you do not need to rely on friction to turn. Okay, the normal force of your car pushing on the corner can provide enough centripetal force to keep you in the corner, even if it was covered with perfectly frictionless ice. Right? Now, it would still be difficult to traverse it because your speed could not change in the slightest while you were going around the corner if it was perfectly frictionless. Okay? Obviously, in the real world, it's never perfectly frictionless. Sometimes it can be close, okay? But it's never perfectly frictionless. Okay? The other reason is bank curves take up less space. You can make them tighter because you're banking them. Right? So you can just say, all right, well, we're going to make this corner 40 kilometers an hour, but we can only make it this big, so bank it so that it takes up less, so I can make it tighter. Right? And that means that you don't need as much land to make interchanges and city planners like that because then it costs less money. Right? All right, same thing is true as I was saying before with the wings of an aircraft. Okay, each wing provides half the lift to keep the plane flying. But as soon as you bank those wings, okay, now your lift is still directed perpendicular to the wings, okay, because it always is, right? But that means now that it has a vertical component that's keeping you aloft, and it has a horizontal component that is directed towards the center of the circle and is going to cause you to move and turn. Okay, so as soon as you bank those wings, even the littlest bit, okay, you're going to start to turn because some of that lifting force is now directed towards the center of the circle. Okay. Everybody all right with that idea? All right, so here's how the banked curve works. Okay, it's an inclined plane, which we're familiar with from Unit 2. Okay, in an inclined plane, you have the force of gravity, which is this line here, the red line. Okay, that's force of gravity. And you've got normal force, which is this line here. Okay, now normal force, okay, always acts perpendicular to the surface. Okay, and so that's what we're showing here. So now this black line here is our normal force. Okay, we've just drawn it above the inclined plane. We've always drawn it below. Okay, now we're drawing it above. Well, that normal force has a vertical component that is equal to gravity. Okay, so we're not falling. And we have a horizontal component that is acting as our centripetal force. So there's a centripetal force, and there's this force that's offsetting gravity. The vertical component offsets gravity, okay, and we have our normal force here. Now, you're probably looking at this and going, okay, Coder, if this vertical component offsets gravity, how come normal force is always smaller than gravity when we draw this triangle? Okay, and that's a fair question. The reason is that when we draw this triangle, this object is not going in a circle, which means it has no inertia that's trying to leave the circle. Okay? When you're moving on this inclined plane and pushing into it because you're going in a circle, you increase the amount of normal force. Okay? So it's now greater than the force of gravity. Okay? Everybody all right with that idea? So the triangles aren't exactly the same, but they're kind of the same. Okay? So this side here is our opposite side. This angle is the same as the angle of bank. Everybody okay with that? Okay, so opposite side is centripetal force. Adjacent side is our force of gravity, okay, and then we got normal force, okay, acting as the hypotenuse. All right, so if I want to calculate the angle of bank, okay, because that could be an important thing for me to know if I'm architect and I'm designing this banked curve. I would need to know what angle I need to bank it at. All right, so that means I need to find theta. Well, I have the opposite side and I have the adjacent side, right? If I go opposite over adjacent, can I find theta? Okay, so the tan of theta equals the opposite side, which is mv squared over r, divided by the adjacent side, which is m times g. Okay? Now, if I'm looking at this formula here, okay, really what's happening is this. Mass cancels. Is that important? If I'm designing this ramp, it's crucial that mass cancels. Why? Is it? Exactly. No two cars traversing this corner are going to have the same mass. This corner needs to affect every car equally, regardless of its mass. Because I could have smart cars, motorcycles, and semi-trucks using this same corner. They all need to be affected by this corner in the same way. Okay? So it's important that mass cancels and that this angle is only reliant on how fast I want them to go, how much room I have for the corner, and whatever the acceleration due to gravity is, which is kind of fixed already. Okay? All right. I got 10 minutes left? Okay. Now, you're never going to be asked to derive this formula. This formula is on your formula sheet. Okay? This is the banked curve formula. The tan of theta equals v squared over r times g. Okay? That is the formula that calculates the angle of bank or anything else for a banked curve. Right, so this is what I just illustrated to you. Okay? FC is the normal force times the sine of theta because it's the opposite side. Okay? And that's equal to mv squared over r. Okay? And then we said that the adjacent side, normal force times the cos of theta, is equal to gravity, okay, which gives us this. So I showed you that derivation, but I showed it without this part in there because I find that that's confusing to people. Okay. All right. Okay, so it indicates that for a given speed, centripetal force needed for a turn of whatever radius you select can be obtained from the normal force by banking a curve at an angle. Now, the more you bank that curve, the more normal force you can get. But the more you bank that curve, the faster you have to go. Why? Yes, that's part of it. Okay? Here's the other part of it. If I make this steeper and steeper and steeper, what am I more and more likely to do? Slide in. Okay? So I have to go faster in order to increase my inertia, that is my desire to leave the corner, so I push on the corner harder, and the corner pushes back harder on me, okay, in order to keep me pinned against it, just like the gravitron. Okay? If you get this thing to be vertical, it is the gravitron, and you have to go really, really fast in order to not fall back down. So there's kind of a sweet spot, okay, for banking curves, okay, that makes them practical. None of the exit ramps or anything that you would use are going to be banked like a NASCAR track, okay? Because it's not practical. And it's not safe either, because now you're saying to people, hey, take this corner at like 80, okay? It's this really tight corner, but take it at 80 because, well, we didn't have a lot of room, so we just made it really steep. Okay? That's not safe, it's not responsible, so we would never do that, okay? The other part of it is, it would be impossible to maintain it, okay? Imagine a snowplow trying to maintain and remove snow and ice from a banked corner that's banked at like 20 degrees. And I know 20 doesn't seem like a big angle. Most banked corners are low single digits. Okay? A 9-degree banked curve is actually pretty steep. Okay? It would feel steep if you were on it. Okay? So they're not banked very much. They're banked just a little bit. Right? Now a NASCAR corner, it's banked a lot. In fact, when they pave the NASCAR corners, they have to hold the paving machine on the corner with a crane. because they're so steep that the paving machines just want to either tip over or slide in. Okay? So they actually have to put a cable on them and use a crane to pull them into the corner and keep them on there so that they can actually pave those corners. Okay? It's crazy how steep they are. All right, so if we're looking at how to calculate the angle of a bank curve, this would be a ridiculous bank curve because it's 13 degrees, okay, really, really steep. Determine the angle at which a frictionless curve has to be banked for a speed of 35 meters per second and a radius of 550 meters. Okay, so tan of theta equals v squared divided by r times g. We're looking for theta, okay, so we have to bring the tan over. So it'll be theta equals tan to the minus 1, okay, of our speed squared divided by our radius times our acceleration due to gravity. When you enter this in your calculator, make sure you're dividing the top by the bottom and not left to right as you enter it, because that's how your calculator will do it, okay? And it will give you the wrong answer. Okay? So make sure you're dividing the top by the bottom. Okay? And that'll give you 13 degrees for that. Now, 550 meter radius is a pretty big corner as well. All right. Okay, yesterday, this has nothing to do with what we talked about today. Yesterday we were talking about this. The relationship between period and frequency. Okay, period, remember, is the time it takes for one revolution. Frequency is how many revolutions per second, or in whatever the time interval happens to be. Okay, so in this question here, okay, we're talking about like an actual disk, not a solid state, but an actual spinning disk drive, okay, that spins at high speed. Platter makes one complete revolution in 0.00833 seconds. What did they give us, period or frequency? That's period, right, because it told me it's this many seconds for one revolution. So if I want to find the frequency, frequency is 1 over t. Okay, so that's 1 over 0.00833. Okay, that'll give us how many revolutions per seconds, because that's seconds for one revolution. Okay, so 1 divided by 0.008. Okay, spins at 120 hertz. Okay, so that's 120 revolutions per second. Is that pretty fast? It's pretty fast. Okay. All right. If I wanted to get that in rotations per minute, what would I do? That's rotations per second. Would it do more or less in a minute? More. Multiply by 60. 7,202 revolutions per minute. Okay. So pretty fast. All right, let's leave it at that. Please wipe down your desks. Mask up and wipe down your desk, please.